And this is going to solution preparation. Solutions can be prepared from one of three sources. A manufactured, MFG is manufactured. In other words, you order something from the manufacturer, they'll send it to you in certain form, either solid or liquid or gas, if you get a gas sample. So manufactured solid stock, that's one source. A manufactured liquid stock, or third, from a laboratory concentrate. The essence of preparing a solution is quite simple as far as procedures go. In essence, what you're doing is adding a solute to a mixing container and diluting up to but not to exceed a desired volume. So in verbal context, add needed amount of solute to mixing container and dissolve in solvent up to but not to exceed needed total volume. Now I write that out for specific reasons so that you will understand that it's not, if you're making a 500 milliliter solution, you do not just simply add your solute and then pour 500 milliliters of solvent on top of it. Because if you do, the system would be too diluted. What you do is you dilute up to, but not to exceed, the specified total volume. And this is one of the exercises when we go to lab next time. You'll have to prepare a specified solution by putting a certain amount into a beaker and then diluting up to, but not to exceed a certain marker on your mixing container. And so it's very important that you understand this up front in terms of the mechanics of making solutions. Now, the next issue is how much should you extract? If you're working with solid stock, it's an issue of how much should you extract? How many grams should you transfer to the mixing container and then add solvent up to, but not to exceed the total volume of solution? Well, it's a very easy calculation. So here is mass of solid solute needed is mass in grams. This will make the perfect solution. Is molarity times volume times formula weight of the solute divided by what we call a purity factor. Yes, memorize this formula. M is your molarity needed. V is the volume of solution needed in liters. F, weight, of course, is the formula weight of solute. And your PF is your purity factor. which is a decimal fraction. Sodium hydroxide, for example, typically comes in, if you ordered it from a manufacturer, at about 95 to 98% pure. So you have to divide by 0.98 or whatever's the assay on the bottle. You get that numbers off the bottle, assay label or whatever. Go to the books. And anyway, I'll show you right now. Okay. I had to put it in question form anyway. So simply, we're going to make 250 milliliters of 1.5 molar sodium hydroxide. And it comes, as, like I say, in stock. Now, let's assume, let's see, the formula weight of sodium hydroxide is 23, 33, 40. Well, 24. Say purity factor is a 98%, which you would apply a 0.98 to the equation, okay, just to reemphasize that. But typically they won't tell you to use a fraction, decimal fraction. Molarity in the problem is 1.5 molar. Volume needed is 250 milliliters, but it needs to be converted to liters, divided by 1,000, move the decimal 3 places to the left, 0.250 liters. That's formula divided by purity factor. So the grams needed is now equal to molarity times volume times formula weight, and it's expressed in liters, divided by your purity factor. Lose that part right there. So now the molarity is 1.5 molar. Now remember, that is, molarity is moles per liter. So if you were checking the units as you go through the calculation, that would help, knowing that that's moles per liter. Volume is 0.250 liters. Formula weight's 40 grams per mole. Those moles drop out, liters drop out. Purity factor is a percent number, does not have units, so 0.98. And so the amount needed that you're going to dissolve into your solvent is it looks like 15.3 grams. Plus solvent up to, but not to exceed 250 milliliters total volume. So it's a very straightforward calculation in terms of, well, I got a bottle of something, I need to ask myself, how much do I take out and dissolve? And as simple as that. Now, there are many mixing containers, and you'll work with one 100 mil volumetrics, and we'll show you that as we do the demonstration and how things function and what have you. The formula that you use provides you with a volume number, because you started a minute ago with a mass number, so you need grams to extract. Well, in this case, how many milliliters do I need to transfer into the mixing container and dilute up to, but not to exceed, the needed volume? Well, the formula looks exactly the same as the first mass number, except it's divided by a density number. Well, it's actually specific gravity. It looks like this. So volume in milliliters, as a matter of fact, needed is molarity times volume in liters of the solute times formula weight of the solute divided by your purity factor, but also divided by specific gravity. Now, everything we use in our work is in water. If it's not in water, you'd have to use the specific gravity numbers, the density relative to water anyway. But density of the stock liquid equals the specific gravity, grams per milliliter. So specific gravity is the same as density. Of stock solution in grams per milliliter. So just to emphasize that, it's very important that you get that idea. It's in grams per milliliter, same thing. I'm going to recover that space. So specific gravity is nothing but density, but I still have to put the specific gravity. Okay, so we're going to prep 500 milliliters of HCl aqueous solution from manufactured stock that is 37% active in HCl, and specific gravity is 1.14. And so, of course, that's the density. So it's the same as 1.14 grams per mil. And the formula weight of HCl is 36 and 1, 35 and 1, or 36 grams per mole. So the volume in milliliters that we need is molarity, volume, formula weight, purity factor, specific gravity. So we're looking at making, I forgot to put in the 0. Let's make a 2.5 molar. I forgot that, sorry. Okay, molarity is 2.5 molar, and we're making 0.500 liters. The formula weight is 36 grams per mole, and that's divided by a purity factor of 0.37. That's the concentration that you'll receive it, and that's on the assay label. And specific gravity is 1.14 grams per milliliter. So when you cancel out everything, of course, that's moles per liter. That will cancel liters, and liters will cancel there. The only thing you're left with is milliliters here out of this calculation. So in this computation, 2.5 times 0.5 times 36 divided by 0.37 divided by 4 equals 106.7 milliliters of HCl, 37%. Now hear this, please. If you put 106 milliliters, 6.7 milliliters in a mixing container, a beaker, and start pouring water on it, it'll blow up in your face. You hear me? I'm not kidding you about that. There is a specific procedure you need to be aware of in mixing strong concentrated acids like this. It's acid, you pour acid into the small amount of water. And here is the issue. Mixing strong acids solutions. You use a small quantity of water, and then you add your acid. Add acid, that's your concentrated acid, into a small quantity of water. mix, and then dilute to needed volume. That's a big caution in putting things together from strong concentrates like this, because if you try to pour water on top of a concentrated acid, it ionizes so fast, it generates so much heat that it will splash back in your face. And that can be disastrous, to say the least. This section is solution prep from laboratory stock concentrate. Now, the essence of this is simply taking a concentrate and adding solvent to it to dilute to a smaller concentration. So, when we do that, you are diluting a given concentration of solute to a lower concentration value. Now, in explaining this or introducing this, the idea is no big deal, but the essence of it I want you to understand in the following context. Let's say that we have a beaker and we place, say, 10 grams of solute in that beaker, and then we've got it in 100 milliliters of solution. Now, plus then you add solvent up to 200 milliliters, okay? And so now your solution is up here, like that. How many grams do we have in the first beaker? 10 grams. How many grams do we have over here?
10.
The same amount? Absolutely. Does everybody see that? Now that's the foundation. What if we had moles? Say we had moles in here. Say 5 moles. When you dilute it, you still have the same number of moles. So the moles before dilution, now moles is a mass number, okay? Moles before dilution will be equal to moles of solute after dilution. See the logic? Anybody? Everybody okay? Now, how do we calculate moles? Moles is molarity times volume, right? Since molarity times volume expressed in liters. So if moles before dilution equals moles after dilution, then I could put molarity times volume in liters before to equal molarity times volume in liters after dilution. This is called the dilution equation. and is a dominant equation in laboratory exercises in preparation of solutions. We're given a 2 molar lab stock and asked simply how much of that stock solution do I need to transfer to the mixing container and dilute to 250 mils to produce a 0.75. Well, using the dilution equation, molarity times volume before dilution is equal to molarity times volume after dilution. Now, since both sides have the same dimensional units, you can leave this in milliliters if you wish, because they're going to cancel out anyway or lead to that concentration anyway. Only when they are not, like if you were given data in moles over here, you would have to work in liters over here on the other side of that equation. But if both sides have the same dimensions, you can leave them in milliliters. Now that's a unique situation, but you can leave them in milliliters. And that's what I'll do to illustrate this idea. The concentrate is 2 molar. So we have a 2 molar concentrate, and the question is, what volume of the concentrate do I need? And that's equal to the molarity that we're trying to make, which is 0.75 molar solution, and we're trying to make 250 mils of it. So it's a very simple calculation to determine how much you will need. The volume of the concentrate needed is 0.75 molar times 250 milliliters divided by 2 molar stock solution. That cancels and you're left in milliliters. That's how much you need to extract, transfer to the mixing container, dilute up to, but not to exceed your total volume. So transfer 93.75 concentrate into the mixing container and dilute up to, but not to exceed 250 milliliters of that solution. Now, there's a twist in this problem that you may not see. Now, everything I've given you so far is add to the mixing container and then dilute up to and stop. Now, you'll have problems that will ask you, what volume of water must you add to reach this dilution? Well, you're starting with 93.75 milliliters, and you got to go to 250 milliliters. How much water do you pour on top of it to reach that 250 marker? Okay, so you've already got 93.75, so the volume of solvent water is 250. That's the total volume minus what you start with in the beaker, which is the 93.75 milliliters that you already have in the beaker. So essentially you are adding this much water to the sample, 156.25. Added onto the stock concentrate. So yes, keep that kind of idea in your mind, because you will see that type of problem on exam days. Okay, so we're looking for this handout, solution preparation problems, moles, molarity, solutions from solid, solutions from liquid, and dilution problems. That one is the second page in the handout I gave you this morning. Okay, is everybody okay? Yep. Everybody got a copy, doesn't it? Sometimes I forget to give people a copy of it. Okay. Just call this solution prep problems. Okay, so we want to begin working some of these problems on moles and molarity. Okay, it says how many moles of HCl are in 35 milliliters of 0.55 molar HCl solution. So moles is equal to molarity times volume expressed in liters. Now, what it's asking is 35 milliliters of 0.55 molar. Well, the volume has to be in liters. So we have a molar, 0.55 molar times 0.035 liters. And remember that molarity is moles over volume in liters, so liters will cancel out in that case, leaving you with the appropriate number of moles. And I get 0.02 moles of solute. Okay. Your problem should be rounded to the data given to be the lowest, the smaller number of significant figures. Well, both of these are 2 sig figs, so I should go 2 sig. Well, it rounds to 0.2. It's 193. So anyway, if 1.5 moles of sodium chloride are in 125 milliliters of aqueous solution, what is its molarity? So you're given 0.15 mole in ACl in 125 milliliters solution. Make that look like a 5. Solution. What's the molarity? Like that. Well, molarity by definition is moles solute volume solution expressed in liters. So this one is simply substitute and solve. So we have a 0.15 mole of solute and 0.125 liters, and we can compute the concentration. That's 1.2 molar in the solute. Okay. Number 3 says what volume of 0.22 molar sodium hydroxide will contain 2.5 moles of sodium hydroxide base. So what volume of 0.22 molar sodium hydroxide aqueous solution contains 2.5 moles of the NaOH. Okay. So if molarity equals moles per liter, we solve for volume is moles over molarity. And this will give you the volume in liters now. So the moles, let's see, 2.5 divided by a 0.22 moles per liter, and so moles drops out, and so this will give you the number in liters. And that is 11.36 liters. And will contain that many moles. Calculate CA molarity. What does it say? 23.45 grams sodium bromide and 100. Okay. Calculate the molarity of a solution that's 23.45 grams sodium bromide, 150 mils of solution. Formula weight of sodium bromide equals 81 grams per mole. So, by definition, molarity is moles solute over volume expressed in liters. So that would give us, we need to get moles from the mass number, moles sodium bromide, and divide by formula weight. So how many formula weights are in a given mass is always the moles. So we have 23.45 grams divided by 81 grams per mole, whatever that is. Uh, 0.29 mole, and the volume in 150 mils would be 0.150 liters. So now we can do the molarity is equal to 0.29 mole of sodium bromide divided by 0.150 liters. And that's a 1.93 molar solution. For that. Anybody still with me? So what's the molarity of putting this many grams in 100 milliliters of solution? So it's still moles over volume in liters of solution. So, but we need the moles of KHPH, and given 204.22 is the formula weight, then moles of KHPH is moles, grams, 0.2074 grams divided by 204.22 grams per mole. Grams drop out, and that gives us 0.0010 mole. And now we can calculate the molarity, which is moles over volume in liters. And so that's 0.0010 mole over 0.100 liters. So, and we can go 10 to the minus 3 over 10 to the minus 1 molar. You want to do it that way, which is 10 to the minus 3 plus 1. So molar, and that's 10 to the minus 2 molar, or 0.01 molar in KHPH. So that just playing with numbers there. Okay. Based on the data here, it should come out 0.01 is correct answer.
Okay.
I don't know what I'll check these in my notes because I've got them. I may have changed the date on something as I went, prepared something else, and then we'll see how the rest of them goes out. But I'll defend that to the death. How many grams of a reagent potassium chlorate would be needed to prepare 250 milliliters of 2.25 molar aqueous solution? So you think in terms of a practical process. You've been given the task of making this solution. Physically, what are you going to do? You're going to take some solid, dump in the beaker, and add solvent to it, right? Well, in essence, you need to translate that into the problem context, which is how many grams would you need? So in the problem is how many grams of KClO3 will give us 250 milliliters of a 2.25 molar aqueous solution. Over KClO3 aqueous solution. I give you the formula weight is given 122.56 grams per mole for the KClO3, and the purity factor is 100%, which translates to 1.00 that you would put into your equation. So grams of KClO3 needed for your solution is molarity times volume in liters times the formula weight of the solute divided by the purity factor. And so you're trying to make 2.25 molar solution, 0.250 liters. It has a weight of 122.56 grams per mole. And again, remember, molarity is moles over liters, so that kind of justifies the cancellation of units. And 1.00 is your purity factor. So let's see if I got a squirrely answer again. KClO3 solid needed. And you transfer that into the mixing container, add solvent up to, but not to exceed the 250, and dissolve it. And you have the solution needed. And let's see if I got that one right. 68. Well, got one right. Run it out real quick. Okay. So your solution is 135 grams of impure sodium acetate. That's a shorthand, sodium acetate. That's 96.2%. And 225 milliliters of solution. Formula weight of sodium acetate, 82.03. Per mole. So it's the same kind of problem. How much would you transfer into the mixing container and dilute up to 225? So grams of the NaOAC solid is molarity times volume, liters times formula weight, again over the purity factor. Molarity that we're trying to make. Let's see, did I give you a concentration? A solution sodium acetate compared with 135 solution acid. Pure salt solution. I didn't give you a solution. Okay. How many grams? Hang on, this has got a twist to it then. We haven't, I got two unknowns in here. I don't have a molarity. I got to give you a molarity. How about 0.50 molar? Let's just put in 0.50 molar.
So we have maybe not expect
You got to have a concentration. So 0.50 molar times 0.225 liters times 82.03 grams per mole. Purity factor is given to be 6.2, that'd be 0.962. So that would simplify that a little bit more. Times 82.962. I got 9.6 grams. What do I? Unless I've already specified 130 grams, I must have specified it some other concentration. I don't know. I'll check that problem. But if you have a 0.5 molar just divided by the impurity, I don't know. I must have left something out of that when I typed it in. So it should have something else in there. I'll check it. Okay, what volume of lithium hydroxide solution would contain 63.2 grams of lithium hydroxide, 100% purity, having a molarity of 1.55 molar? Well, this is applying the calculation equation. Grams equals molarity times volume times formula weight over your purity factor. Well, it's looking for a volume of solution. So this is, in essence, in this problem, what you're looking for here. So volume in liters, of course, is the purity factor times grams of solute used, certainly divided by the molarity and formula weight. So it's just a simple algebra issue. Now, substituting purity factor, I think he gave it 100%, so that's 1.00. The grams, 63.2 grams, and that's divided by a molarity of 1.55 molar, and the formula weight is 2395. And so running that out, it tells you what volume of solution contains that many grams. I got 1.7 liters. Okay, out of that one. Well, 1.68. Okay, I rounded it up. 1.68, 1.7 liters. Okay. Up from liquid manufactured stock, and you keep in mind the focal point of this is to determine how much you need to extract and dilute to the appropriate volume. However, the application here is for usually for strong acids and solutions of that nature, in which you need to be conscious of how to mix those. Always add acid into a quantity of water, then dilute. So just re-emphasizing the safety factor here is what I'm trying to do. So that was number one anyway in this. What volume of manufactured stock, 37% HCl, would be needed to prepare 100 milliliters of 3 molar aqueous solution? And they got a specific gravity and formula weight in there. Well, volume and emphasizing this also this formula gives you in milliliters when everything's said and done. So this is molarity times volume in liters times formula weight of the solute out of a purity factor and specific gravity number, which is the density of the stock. So we're trying to prepare, where is it, 3 molar solution, and we're making 100 milliliters, which is 0.100 liter. Formula weight's 36 grams per mole, and the purity factor is 0.37 from 37%, and it's 1.14 grams per mil specific gravity becomes density in that. Okay, and remember, molarity here is moles over liters. So the moles will cancel out, liters cancel out there, grams cancel, and so the only unit left remaining is in milliliters, just to emphasize that idea. So there's 3 times 1 times 36 divided by equals, that's divided. Okay, so you have 25.6 milliliters of HCl, 37% needed. Add into small quantity of water, then dilute to wherever we were going, 100 milliliters total volume. So emphasize that enough to hopefully, it'll sink in. So now we're given 50 milliliters of HNO3, 68% stock. And this gives us 2.0 liters of 5 molar solution. What's the molarity of the manufactured? Oh, what's the manufactured stock from that? So there's a couple of ways to work this one. If you have a 68% stock solution and you want to convert that to moles per liter, so one way to work this is 68% is a weight ratio, and so that would mean 0.68 grams per 100 grams of solution is what it means right there. And so what you need to do is convert this to moles of the solute, which is HNO3 in the numerator, divided by volume of whatever that solution is in liters. And so that'll give you that 68. That's the simplest way to do that. And all the other stuff in there, you could probably do it that way anyway. Well, a nitric acid, let's see, I need a formula weight. Did I get that? Well, nitric acid is 48, 14, and 1, 8, 9, 10, 11, 12, 13, 4, 5, 63 grams per mole. right there. So this is 0.68 divided by 63 grams divided by grams per mole. So that gets us to moles in the numerator of that relation. And so we have 100 mils of solution that has a specific gravity is 1.42. I think that's what it said. Yeah, 1.42. Well, that means it's grams per mil. So if you have 100 milliliters times 1.42 grams per milliliter, that'll sounds like give you grams. Let's see, 100 grams. Oh, wait a minute. I'm doing that wrong. It's 100 grams over 1.42 grams per milliliter. Now, that'll give you moles over milliliters, which is not molarity. Okay, so this denominator term needs to be divided by 1,000 milliliters per liter. And that'll give you the concentration of that concentrated acid. So we've got to the top 0.68 divided by 63, and that gives us a 0.011 mole. And I took 100 divided by 1.42, and that's equal to that 70.42 divided by 1,000. And that's a 0.0704 liters. So if you set it up like that so you can see how I made the conversions to the definition, that's all I'm doing. See, I'm taking a 68% by weight solution, which means it's 68 grams of stock of solute per 100 grams. That's what percentage means in the solution, and then converted it to a volume in liters, and then solved that. 0.011. Looks like that can't be right. 0.011 divided by 0.0704. It ain't a 0.15 molar solution, I can tell you that. At 68%, sure, a lot higher than that. Okay, so I made the adjustment here, made that correction, and that's the final answer. I know it's going fast, and I apologize. But all I did was pay attention to that. All I did was convert to that definition. Okay, it says what volume of water must be added to 30 milliliters of 5 molar calcium chloride solution to dilute it to a 1 molar calcium chloride solution. This is one of those problems that I mentioned earlier. It's not what's the final volume, it's how much water is needed to reach the final volume. So if you, okay, so your number one, here you are given 30 milliliters, 5 molar calcium chloride aqueous solution. All right, now how much water solvent will be needed to obtain 1 molar calcium chloride final concentration, like that. Well, this is simply a dilution equation. Molarity times, starts with this anyway, molarity times volume of the concentrate is equal to molarity times volume of the solution. So you want to figure the volume of the final solution, but then you have to turn around and subtract the 30 milliliters from it, because that's what you're putting in the beaker to start with, and then pouring water on the top of it up to the final volume. So the solution, final solution volume is molarity times volume of the concentrate over the molarity of the diluted sample. And so the molarity of the concentrate is 5 molar, and you have 30 mils of that, and you wind up with 1 molar, which cancels out, and so your solution volume ends up at 150 milliliters total solution volume. But the volume of solvent, water, is equal to 150 minus 30 milliliters, which is, well, 120 milliliters of your solvent water on the end of that. So that's a very important problem, because you will see that kind of problem again as we get deeper into the material. 80 milliliters of a 2.50 molar HCl solution plus 60 milliliters of solvent. And so this is trying to apply, what's the concentration? So you got to calculate it in terms of moles over total volume in liters. Okay, the concentration in molar terms is moles of HCl over volume of solution expressed in liters. Okay, let's start here. What are you putting into the system? Moles. Remember the initial example I gave you? I drew the little beakers and said, okay, you got X number of moles in the first, and then you dilute it, you still have the same number of moles. Well, moles is molarity times volume. So the moles of the HCl is molarity times volume in liters. So we have 2.50 molar times 0.08 liters. And so that gives you the moles that'll go in the denominator up here of this problem. 2.5 times 0.08 equals 0.02 mole, 0.20 mole HCl. Now the volume of solution in liters is converting, well, let's just get the volume of solution in milliliters first, because what you're doing is taking 80 and 60, 80 plus 60 milliliters, 140 total volume of solution. There's your total volume, which is now 0.140 liters. So now the molarity, I'll use the brackets, HCl final is moles, which is 0.20 mole over 0.140 liters now. And that's divided by 0.14. And it's a 1.43 molar solution. And so I didn't think I could make it. All right.